Hello, I'm Silvia Zorzetti, Senior Engineer at Fermi Lab and the Ecosystem Deputy Lead for the Superconducting Quantum Materials and Systems Center. I'm delighted to moderate this panel, Quantum for the People, Connecting Quantum Information Science and Society. The panel features scientists affiliated with the Department of Energy National Quantum Information Science Research Centers. Quantum information science and technology is an emerging field. As such, we are here to discuss with our panelists the impact and breakdowns on the society and education. Before I introduce our esteemed panelists, whose talk are available on the AAAS meeting website, I would like to remind the audience that you are very welcome to submit your questions through the Q&A chat. I would also like to remind that as a registrant, your attendance at or participation at the AAA annual meeting sessions means that you have agreed to permit AAAS to use and distribute, both now and in the future, your image and or voice in photograph, video, audio, and electronic reproductions as such event and activity. So please be mindful of this and as you participate. So now let me introduce our panelists for this session. Alexandra Boltasseva is Workforce Development Lead for the Quantum Science Center, which is also Department of Energy National QIS Research Center, led by Oak Ridge National Laboratory. She's the Ron and Dottie Garvin Tonjes Professor of Electrical and Computer Engineer at Purdue University. Welcome, Alexandra. Charles Brown is the Stamper-Kern Group at the University of California, Berkeley, an institution partner of the DOE's Quantum System Accelerator, which is co-led by Lawrence Berkeley and Sandia National Laboratories and is integrated by 13 other partners. Welcome, Charles. Monika Schleier-Smith is an associate professor of physics at Stanford University, a MacArthur Fellow, and a member of QNEX, the Department of Energy QIS Research Center led by Argonne National Laboratory. Welcome, Monika. So, panelists, before we open our session to audience questions, would you give us a summary of your spotlight talk? I would like to start with Alexandra.
Sure. Thank you very much, Silvia, and welcome everyone. I'm very pleased to be here, and thank you for AAAS for holding this panel. So we are all very, very excited. As Silvia said, I am affiliated with Purdue University. I am also a workforce lead at the Quantum Science Center, led by Oak Ridge National Lab. And I also lead a new center at Purdue, Elmore Center, Frontiers for Research on Crossroads of Quantum and AI. And incidentally, that's a topic of my talk and what I would like to discuss today. Because I believe that with the ongoing rise of quantum devices and quantum technologies and quantum hype everywhere, what we should do, we should leverage the concurrently happening revolution in big data, machine learning, and artificial intelligence. And I do believe that these two revolutions, both in fundamental science and breakthrough applications, should go hand in hand. We should leverage advances in classical machine learning and AI to push forward the frontiers of quantum science and quantum devices. And we should use and plan how to use the power of emerging quantum computing to solve the long-standing problems of AI. And I believe that making it accessible to general public, our discussions and viewers on the impact of these two technologies on fundamental science and everyday life would actually lead to the creation of a new emerging quantum AI society. And in a way, it's already happening. We have smart devices all around us. And I think it's not far when we will have quantum toaster in each kitchen. And I'm words from CEO and founder of one of the very successful quantum companies, Dana Anderson, who leads Gold Quanta. I'll pass it back to Silvia.
Thank you, Alexandra. Charles, would you like to go next?
Yeah. And let me add some information too. So first off, thanks to AAAS for organizing this. Definitely very happy to be here having this conversation. I think this conversation is very important. So yeah, I'm a postdoc in Dan Sember Kearns Group at Berkeley. And I think it's also, in the context of this conversation, important to say, starting next year in 2023, I'll be starting as an assistant professor at Yale. So in my talk, I mentioned this really incredible world of quantum materials. And quantum materials are really special because they are materials that have these really interesting properties that can't be described with classical physics. In the world of actual like solid materials, these are solids with exotic physical properties that emerge from two particular things, I would say, that is coherence and entanglement. And so I did a little bit in my talk to sort of describe those things and why they're interesting. In particular, I mentioned sort of two different types of potential quantum materials have, and I broke them into scientific potential and technological potential. On the science side, there's this big question of how this notion of quantum fluctuations lead to order in a system, and how maybe quantum fluctuations push a system to exist in some interesting or exotic state of matter. Or what is the role of mathematical topology in quantum materials? It turns out that there's actually a lot of overlap, and topology tells us a lot about some really interesting properties of quantum materials. On the technological side, they're really important, future devices are, kind of have them now, a quantum computer, want to develop this further, or quantum enhanced sensors, or a really lofty thing related to like power transmission. And that sort of, is related to, these notions of high temperature superconductivity. But I also talk about how, quantum materials are being developed all over the world. And this is really important. And it's also important for us to think about who is developing them. I mentioned that if you sort of look around the quantum landscape, at least here in the United States, the workforce as it is, whether that's sort of who is in industry right now, or who is a student or postdoc or faculty, and who is training upcoming workforce, they are not particularly diverse, and this is something that we need to work on. And I mentioned how it's really important to do so because of sort of how our technology-based/driven economy is so dependent on STEM. And when you look at this particular sort of subset of people referred to as early career doctorate holders, these are people that are within 10 years of having earned their PhD, and people who like really drive the direction of the field. We are really lacking diversity there. So I hope to develop some more of these ideas as we go forward in today's session.
Thank you, Charles. Yeah, we'll certainly do that. And also congratulations for your career advancement. Monika, can you summarize your talk?
Absolutely. So it's a pleasure to be here. In my video, I introduced atoms trapped by laser light as model systems for studying quantum mechanics, and as a really powerful platform for a range of applications, from ultra-precise clocks to future quantum computers, to simulating a range of phenomena from the electronic materials that Charles mentioned, to really fundamental questions in quantum gravity. And in particular, I zoomed in on this question of simulating fundamental questions. So, for example, in the same way that we know matter and its properties emerge from building blocks that are individual atoms, could it be that the fabric of space-time itself, curved by gravity, fundamentally emerges also from discrete constituents? So can gravity emerge from quantum entanglement? In my lab, we're building to explore this question. Those toy models consist of clouds of atoms with interactions that we can program in a flexible way using laser light by letting atoms talk to each other with the aid of photons. So that programmability has allowed us to explore this question of toy models of gravity perhaps emerging from quantum correlations, but we're also interested in that as a tool for a range of quantum technologies, from ultra-precise sensors to quantum computation. And so in that vein, I mentioned there are lots of hard problems to be solved and lots of exciting opportunities for not only the current generation, but also the next generation. And educating that next generation is another area that I'm quite passionate about and that I touched on in my talk.
Thank you, Monika. Maybe I can give you a follow-up question on that. So what in particular excites you at the moment about the growth in the field and in this technology, and also, you know, how can we make this technology more attractive and impactful for the society?
Yeah, great question. So, you know, I think what I'm excited by are both the challenges and also the opportunities. So, you know, fundamentally, one thing that we know about quantum systems is that as soon as you have something like 60 quantum bits, that system is impossible to describe on the world's largest supercomputer. So there's this fundamental challenge that brings up questions of, you know, how should we even think about and visualize these systems, but also is the reason why we expect these systems to have power beyond the capabilities of classical computers for computation. And there's really great opportunities now to start to sort of bring together the people who are building the hardware with kind of the people who are asking fundamental questions about how does one with necessarily imperfect hardware solve problems like correcting errors, and what are the applications that once we bring all those things together can be addressed? Can we solve problems from chemistry that will ultimately have perhaps applications in drug development that will have societal impact? Can we solve material science problems that will allow us, as Charles touched on in his talk, to have perhaps you know, high temperature superconductors that will transform electronics and power distribution. So these are all hard problems that really require interdisciplinary thinking. And I think that's a really sort of exciting opportunity now, is to bring together perspectives from different fields and have sort of a common language to ask, how can we take advantage of our increasing control over quantum systems to solve those problems?
Thank you, Monika. So related to that, I would like to make a question to Alexandra, as she's here, as she's professor in Purdue, and she's also workforce development leader at the National Quantum Information Science Research Center, which is led by National Lab. So my question is, what can we do as you know, representative of National Lab, Quantum Information Science and academia to promote the education in quantum information science? If a young researcher today is, or just a high school student today is listening to us, what kind of path can we recommend to him or her?
Sure. I would actually like to build on what Monika just said and focus on my attention on the fact that we really have to make sure that for training the next generation of engineers and scientists for the quantum science and technology, we have to make sure that we expose the students to this multiple disciplines, and we start early in the career paths and education path. So that becomes increasingly important. And to start with, if we'll try to define right now, what are the skills and what are the qualifications that are required to enter the quantum field or quantum industry, we will actually end up having a pretty long list of qualifications that might be required. And they will all be different because there are so many facets in the emergence quantum science and technology, and it is multidisciplinary in the heart of it, right? We are talking about low temperature physics, material science, computational approaches, theory, experiments, and all together. So as going back to my topic, what's important, and it's emerging quantum physics and increasingly important. And I see that our task is, first of all, to make sure that we are creating this learning environments and exposing the students to this multidisciplinary environment and helping them on their way to choose the right path, we have to create a different curricula. We have to create a different pathways to earn degrees in quantum engineering. And many universities across the country are already doing that. So we are already making ensuring that we are providing the right multidisciplinary learning environment. Another important thing that I would like to mention, and as you said, I am also representing not only Purdue but the DOE-funded quantum center with many national labs involved. We have to make sure that we address the training of the workforce on different levels. So, for example, the way I think about it is we can distribute the opportunities and load a little bit so that the DOE-funded centers naturally focus on educating graduate students and postdocs and training scientists through exchange programs and multi-dimensional workforce development initiatives. While, for example, National Science Foundation centers, and we again have many of those that have already successfully started to invest into quantum workforce, they would focus more on creating new undergraduate curricula and K-12 education. We will have to align these activities. Obviously, we have to build synergy between these two so that we can coherently go out to general public. So outreach events would also be extremely important. We have to leverage all our knowledge about creating undergraduate and graduate curriculum, our knowledge of how to reach out to broad public via different channels, lectures, and social media. And ultimately make sure that we are both training the next generation of scientists and engineers, but also creating this quantum culture and demystifying quantum at large.
Thank you. We have our first question in the Q&A. I just want to remind the audience that if you have any questions, so please submit it in the Q&A chat. So we have a question from Erin. She would like to hear from the panelists about what can the broader scientific community and members of the lay public do to help improve access and equity in the QIS space. Maybe we can start answering with this question with Charles, because he also covered some ideas about having this field more inclusive for underrepresented group. But also Alexandra and Monika, feel free to jump in anytime.
Yeah, so thanks for asking this question. I think this question is super interesting, very important, and very hard to answer. And I think it's a full answer to it probably takes part in many different parts of society, several of which aren't like directly connected to academia or government. So what do I mean when I say that? I mean, like when I think of trying to get people excited, or maybe more people excited, maybe younger people excited about quantum information science and technology, I think of how I wish we had someone sort of like Carl Sagan on the quantum side that could like really speak to the imagination of people. I think that would go a long way. And I think it sort of makes sense to have this on the astro side of things, because, you know, you can walk outside and look up and see that there's a bunch of stuff out there that's very interesting to you. And I feel like it sort of naturally makes you feel a sense of wonder. But unfortunately, it's a little more difficult to get that on our side of science, because you can't just walk outside necessarily and feel really inspired by, you know, a piece of diamond or, you know, a microchip that has some interesting components on it. You know, I'm not so sure. But if we had someone who could like really like be like a spokesperson for quantum information science and really connect the general public, I think it would do so much. More towards the question of, and I don't want to talk forever, so I'll stop shortly. More towards the question of like, you know, access and equity. I think that there's a couple things we could do. We have some very much untapped pools of talent in the United States. We'll just talk about here in the United States. In particular, the system of HBCUs, historically Black colleges and universities. And actually now IBM has created this IBM HBCU Quantum Center along with several HBCUs, where the goal is to develop quantum information science among the HBCUs, get HBCUs connected to the powerhouse quantum initiatives happening around the country. And so I think that doing that on sort of a bigger scale is really important. And I also think that, you know, we have this complicated problem here where like educational resources are tied to things like taxation. And you find that certain regions of the country have different demographic makeups, where maybe a certain ethnic demographic or certain ethnic demographics, you know, end up in schools that benefit less from having tax money pull into providing them with educational resources that allow them to be on a trajectory where going and doing quantum information science is possible. So I think that part of the answer is restructuring how schools are funded, making sure that there's better public funding for education from the very beginning. But I'll stop there for now.
I would like to comment also, so there are a couple of questions in the Q&A box, and there is one through all of them, and it's true that right now when we think about quantum science and technology, the first thing people that comes to mind is actually physics PhDs, right? So that's people we work with, and that's whom we hire, and that's the people who can speak and feel comfortable about quantum, and the only audience, so to say. And we have to change that. And I think that ultimately we will start changing that, and rather early in education. And even starting with school kids and training teachers, providing seminars and training courses for teachers that not even high school, even before that. And I know again many universities are investing and putting tremendous efforts into creating classes for kids and teachers that teach quantum without any math. And if we think about it, we can start pretty early. For example, just by switching from deterministic education to probabilistic would probably be already easier for kids later to enter the quantum thinking. So there are multiple things that can be changed even in middle, if not elementary school, and how we teach to make this entrance barrier to quantum less pronounced and make it more accessible. And I am aware of several programs across different universities that starting to focus on educating teachers and creating these programs for YouTube and for lectures for kids that don't even use math. And if we have this available, then it will be accessible to many more, not only students and kids, but also lay audience.
Thank you, Alexandra. And just, as my thought is also, having kind of education which is perhaps not really related to math, but more to the idea of a new technology and how does this develop can also go beyond quantum itself. So it can also include other disciplines, like you mentioned, AI and so artificial intelligence and machine learning. Monika, did you want to?
I would love to just amplify this idea of the importance of kind of early exposure to perhaps quantum, but even generally exciting cutting edge topics in science and in physics. So in my own teaching, I teach freshmen quantum information, but that's a start, but that's not early enough, right? First, they have to even get to the point of being college freshmen who think that's what they might want to learn. One of the things that I've enjoyed kind of watching is that a number of my undergraduate students actually have taken things that they've learned in their classes and actually extended that to outreach for high school students from a range of backgrounds and from all around the world. And actually, COVID has taught us that this can even be delivered virtually. And so it's kind of fun seeing that impact kind of amplified and extended to younger students. But the other thing I just wanted to comment on is, as part of kind of reaching students early on, this is also an opportunity to kind of just convey the possibilities that are out there. So just if I look at actually colleagues in my physics department, a number of them are actually, their parents were also physicists, right? And so of course, if your parents are physicists, you know that's something that you could do. But there are so many people who might not even realize that that is a career option, realize things like that you actually get paid to go to graduate school, right? You don't need to be independently wealthy to go into science. How you sort of even go down that path, the importance of getting involved in research early on. I was really fortunate to actually in my summers in high school get paid to do research, which is sort of not something everybody gets to do. But I think the more we can make those opportunities available to sort of get into science early on and get connected to the community, that is something that will really help enhance who's becoming a scientist and who's participating and pushing us towards these quantum technologies.
Thank you. So we have several questions in the chat, in the Q&A chat. So some partially were already answered. So Akshay was asking if there is an effective way of promoting quantum technologies to younger audience to get them excited about upcoming science and technology. And he say he can't even imagine to how to get people, going beyond things like Schrödinger cat. Maybe something that we can think about is how can we visualize, how can we, make people visualize quantum, as Alexandra say, like we can all have a quantum toaster at some point, or Charles and Monika spoke about superconducting materials that, can be accessible. So, so in your opinion, and I leave it open. I don't know who wants to answer first. So, what can be like a first technology that can be, accessible in the next decade to the people, just to, to make the society visualize quantum actually?
Mm-hmm. I may jump with the first example, and I think where we can start, let's say, not demystifying quantum. I agree with Nicholas. We should keep some mystery there to encourage people and to get them motivated. I'm not against that. I truly think it's fascinating, and we should keep it this way. But we should make sure that we are not scaring kids away, right? Because especially for girls, and I know that many girls would say, well, that's too hard. I would stay with something more tangible like material science. And so we should make sure that we give examples of quantum science and technology which can be felt, and go beyond the Schrödinger cat. An example that comes to my mind is quantum sensing. Every time we talk about quantum, immediately people, especially those that are far away from quantum science and technology, the only thing that comes to mind is quantum computing. And people would say, well, this is it's too hard. They're not available right now. It's just out, right? But quantum technologies, quantum science is not only about quantum computing, right? We know there is a fascinating research in quantum materials. There is quantum communication systems, it says security, and that's quantum sensors. And I believe that quantum sensors, and we already have, elements of that, and what we would call the quantum sensors around us already, would be the first that we would use. So how about we educate people that we can really go down to sensing with extreme sensitivity, something just using quantum properties of light, or using light sources that emit just a single photon on demand. We are really going down to such a low levels of intensities that we are counting photons, and that's quantum. That's realm of quantum science, and that's the technologies that, for example, would open up possibilities for achieving extreme sensitivity in our sensors, in imaging, including space exploration and other areas where people might already feel more comfortable in.
Thank you, Alexandra.
Can I add a few thoughts to that, actually?
Yes, please, Monika.
Yeah, I love this example of quantum sensing because quantum uncertainty is one of the things that first excited me personally about quantum mechanics. I learned in chemistry that the position of an electron is uncertain in an atom, that you don't know where it is and how fast it's moving at the same time. I found that idea kind of fascinating, and there are sort of nice visualizations that can help us relate to the idea of quantum uncertainty. But also, I love this example of photonics and also quantum communications. So when I teach freshmen quantum information, some of the first examples I give are how do you use a photon to securely convey information, send information in a way that is fundamentally eavesdropper proof. And that's something where in just a couple of weeks, we can really sort of develop some intuitions for why that's possible, and even do some hands-on optics demonstrations to learn things about how measurements work in quantum mechanics and why that allows you to convey information in a way that's fundamentally secure. And so these are things that you can really get to without too much math and in a very intuitive way.
Thank you.
Can I actually also add to this?
Yes,
so I think
please.
this is a really important one. I wanted to make a couple of examples. So I really like that. I also really like the example of photonics being brought up by Alexandra. So one thing that I think can really help is like trying to show people how what feels like very abstract or lofty quantum ideas are directly connected to things they already care about a lot. So for example, one thing I think is amazing is using quantum properties of light to do better imaging. So light has amplitude, which is sort of like brightness, has phase, it says something about its frequency. You can plot these things versus each other, and you have some sort of noise that gives you a certain shape. People have figured out how to squeeze that noise pattern in one direction, where you can suppress the amplitude noise. That's allowed people to image sensitive biological samples with less light, getting better quality images without like damaging these sensitive biological materials. Being able to image biological materials is super important. We know a lot of, for many reasons related to the pandemic, we all know very keenly how important it is to be able to further advance our ability to understand biological systems. That's one. I also really like the high temperature superconductivity one. So that's really lofty, but imagine we had them. Imagine that we could really distribute power further for cheaper, right? There's a way, depending on how, power and politics works, that many more people could have access to power in a way that's really transformational for their lives. And I think people care about improving like quality of life, or like improving our condition as human beings. So I feel like if we can relate even the most lofty of quantum ideas to stuff that we feel viscerally, I think people will be very excited about them.
Thank you. We have a couple of questions from Philip in the chat. I hope that, the first one question, if the speakers could give like a good conceptual description of quantum information science, it was answered with these examples that were made by Alexandra, Monika, and Charles. Philip also has like a question. Can the human eye be thought as a quantum sensor? I see Alexandra answered, so maybe you can expand more.
That's a great example. We can detect amazingly just a couple of photons down to one, and that's fascinating, because one of the challenges in quantum science and technology, creating practical quantum sensors, including single photon detectors. And single photon detectors would soon be part of many sensors that we'll have around us, and both for bio and medical imaging, for applications in astrophysics and many others. So we need those. And as in many cases, sometimes nature is the first. And there are very sensitive things and exotic physics that is still around us.
Thank you, Alexandra. Just say something about quantum sensors from superconducting. So there are quantum sensors that, for some extent, already are used in the lab, for example, to detect dark matter and axions. So these sensors are so sensitive to like single photon level, which is very, very little radiation, that we can think also to employ them, for example, in weather forecasting and other kind of activities that are very close to our life, our daily life. Okay, so we have a question from Adam. This was about the workforce development. We kind of stripped through sensors, and so I left this question behind, but probably we can answer this now. So Adam say physics is the only discipline that focuses heavy on quantum information science, and typically mostly at the graduate level. Do we need the new degree programs to train the new QIS workforce rather than just relying on the physics PhD? So Alexandra, I know that you touched this in your introduction, so you can expand.
Yes, and I would like to say that definitely, and many schools are already creating the programs where it will be both physics and mathematics and computer science involved, because this would be the necessary training skills that we would ultimately need. To give you just a simple example, like my group, we are trying to merge the areas of quantum photonics specifically and machine learning. And it's very hard. It's very hard to find students and postdocs who are trained in both. So what we would usually do, you start with a physics or engineering PhD with a background in electromagnetic theory and modeling, and then he or she would learn machine learning, and the other way around. But that's what ultimately we should be striving for. And I believe that bridging computer science and quantum is extremely important, but because there are so many points of contact and points of strengths that we should leverage upon, that it is very necessary to start with. As I said, we have to leverage advances in machine learning to push the frontiers of quantum science and devices, but we also have to start using our quantum simulators for solving problems for AI. And that's exactly what's happening right now, and creating new programs will help us to get a steady flow of new students into this interesting and challenging fields.
Thank you, Alex.
Just to add to that, I think, and I touched on this earlier, there are very few people who have a deep understanding of the hardware, the sort of algorithms and the applications. So for example, we'd like to solve chemistry problems, and there aren't that many people who know like what is really the hard part of the chemistry problem that would need a quantum computer, and what is involved in the hardware. There are different hardware platforms, and what is then the most natural way to sort of use that hardware to solve that problem, and sort of understand from the algorithmic side how to bring all of that together. So this idea of like a new degree programs where people get trained in sort of different aspects, and that Sasha mentioned physics and math and computer science, but also I would add chemistry, electrical engineering, material science, right? And not everybody is going to be a jack of all trades, but even having just more people who know like two of those things really well and different combinations of those things, I think would be very powerful. And interdisciplinary degree programs could be a great way to build up that expertise.
Yeah, thank you, Monika. Yeah, so we have another question in the chat. I would like to pose this question to Charles first, because he mentioned before about underrepresenting groups and kind of going to elementary schools, and these are things that maybe we cannot address directly, but so beyond. So the question is from Tomotaro. Beyond improving public K-12 education, I'm wondering what opportunities you see at the undergraduate and graduate level to improve diversity and equity, particularly in physics. And Charles, I remember that you had some practical ideas on that during your talk.
Yeah, so I have a lot of ideas on that. That's something I think about a lot. So where to start? I think, so at least among the most important things for me, specifically on the academic side, is improving like the number of role models that students have and their access to them. So I think that sometimes, at least in our discipline, we don't place enough importance or have enough understanding of the fact that role models are immensely important. And every now and again, I come across a comment where, you know, someone says to me, oh, you know, I feel like Black people, for example, just aren't that interested in science, or, you know, something to that effect. It also turns out that in society, a lot of role models that young Black students see are not scientists. So my answer to this is, you know, I should be one of these people that is more visible so that I can serve as a role model, so that, you know, as Monika mentioned, these young kids coming up can see that, like, one, being a physicist is something that you can do. That's a real job. And I can get paid literally to do experiments to try to understand mysteries of the universe. It's an incredible thing, right?
And I just, sorry, I don't want, it's a cool job. So, you know, some people think that physicists and engineers might be just nerdy people in the lab, but I think we do pretty cool things overall.
Absolutely. And maybe I'll just make one more comment and, you know, yield the microphone. I think that it's important to make sure that, like, okay, so another problem that happens in a lot of places is that people end up being the only one of their sort and not having enough resources in the form of, like, people to, like, relate to or rely on that really understand their perspective, that really have their that really has their perspective understood and respected. And so I think that, you know, when you're talking about things like diversity and inclusion, it doesn't make sense to just, like, hire one of these bring in one of these underrepresented people only for them to be immensely isolated. It's really important that there are cohorts, or if they're not, that, you know, they have access to mentorship that understands them. I can say that, you know, let me finish with this actually. Mentorship is super important. And many of my most important mentors do not share several of my identity aspects. For example, two of my most important mentors are a white man and a white woman. And I think it's really important that people are able to identify, like, certain people who, one, look out for them and have these, like, skills or resources that they need and know how to, or can, like, develop a sense of how to have, like, a mutual relationship, a symbiotic relationship where you can, like, I don't know, get the things you need from people who don't necessarily share all of your identity. I'll say it that way. I think that's clear enough.
Yeah, I agree with you, Charles. So Alexandra and Monika, I would like to ask you if you have something to add. We are almost hitting time. Okay. So our time is nearly up. So I take the opportunity to thank Alexandra, Charles, and Monika for their thoughtful comments. I also thank AAAS for hosting this session on quantum information science, and thank to the audience for their interest and insightful questions. We appreciate hearing from you. Please enjoy the rest of the conference.